images of a star created from nothing, 2 images, and then they come apart. This is due to something called a caustic in the path light cone of the camera, to use a very, very fancy language. So one of the projects that we did with the computer program that my colleagues wrote for Interstellar, we studied these caustics and the creation and destruction of multiple images. So if you look down here, just watch, you will see down there, you just saw 2 images created, came apart. Then if you watch the very end of this film clip, you will see this image annihilate with another image, not with the one that it was originally created by, but with a different image. So images are being continually created in pairs, and they annihilate in pairs. And it's really very beautiful to watch and interesting to study mathematically. And so we wrote a paper that describes the full details of it. When you look closely, you see up to 14 images in this team's simulations, up to 14 images of a single star here. And you can watch them in pairs created and destroyed. But that's not what Interstellar, what the black hole looks like in the movie. This is the black hole in the movie. And what is the difference? The difference is that this black hole, gargantuan, has a disk of hot gas around it, like Saturn's rings, but very hot, that is very bright. And that bright disk outshines the stars, so it's like trying to look at the stars in the daytime with the sun shining. You just can't do it because of the bright light coming, in this case, from the disk. Why does the disk have this strange shape? And that's what was commented on in that first film clip I showed you. Very simple. Here is what the disk actually is, much like Saturn's rings. Here is the IMAX camera. And in our calculations, a light ray emitted from the top of the back of the disk, opposite the camera, it is bent by the warped space around the black hole, warped space and time, and comes down to the camera like that. So the camera sees the top back of the disk as though it were here. And a light ray from the bottom back of the disk comes around the black hole, comes up to the camera, and so the bottom back of the disk looks like it's there. So this is the top face of the back of the disk. That's the bottom face of the back of the disk. And here, the light from the front of the disk just comes directly to the camera and produces this segment. There's one other thing, however, occurs here. If you were looking with your eyes, you would not see this there. The disk would have a rather sharp edge. But Christopher Nolan insisted, we're showing a movie, and everything that you simulate on a computer has to be done as though it were seen not by the human eye, but by an IMAX camera. And so, first the image was computed, and then it was sent through a computer program, and in technical terms of optics, it was fed through the point spread function of the IMAX camera's lenses. And what that did was the light scatters in the lenses of the IMAX camera, and that produces this fuzziness around the black hole. And so they measured the point spread function. For people who know the optics, they measured the point spread function of the IMAX camera that was used, and then they processed the image according to that to get precisely what this would look like to an IMAX camera. From some things that I will talk about in a few minutes, we know, in fact, that this black hole is 100 million times heavier than the sun, and its circumference is the same as the Earth's orbit. So it's a giant black hole. A black hole of just this size exists in the center of the galaxy Andromeda, which is the nearest big galaxy to our home, just this same size. Now I will return to that. Where do accretion disks come from? They're created when a black hole tears a star apart. So I will show you a film clip from a computer simulation not by Hollywood people, but by two young astrophysicists, actually postdoctoral scientists, James Guillotin and Subi Jazari. If you look up here, if you look very carefully, there's a little tiny blue dot that is the black hole. There is a star that is going to come in, go around that tiny blue dot, and be torn apart. And you will see what happens when it gets torn apart. We're watching from some great distance. So there it was torn apart, and now the gas is thrown out in a large jet. Some of the gas is captured by the black hole to form a disk, but much of it just escapes into interstellar space. And you wind up with a very hot disk. That disk will normally have a temperature of 10 million or 100 million degrees, very, very hot. That's too hot for the actors in Interstellar to survive. And so for Interstellar, we assume that the disk in Interstellar is very old and very cold, about the temperature of the sun, so that the actors could get reasonably close to it and survive. Astronomers do not see such old disks, so they don't see disks that look quite like the one in Interstellar. The one in Interstellar is what you would see if the disk had a temperature of 4,500 degrees Kelvin. There is a black hole at the center of our Milky Way galaxy that weighs about 1/25 as much, 4% as much as the Gargantua. So it's small in that sense. It's still 4 billion times heavier than the sun. These are orbits of stars around that black hole. This is now observational data taken by the research group of Andrea Ghez at UCLA, using mostly the Kep telescope. And she's made a film where you see the stars moving in their orbits, and you look down here, you see a star come in, flick around the black hole. By looking at how these stars move, you can see where the black hole is located, and watch the stars be deflected by the black hole. And it's from these orbits that she has been able to weigh this black hole and find that it is 4 billion times the mass of the sun. There are actually possibilities to see the disk and the shadow of this black hole in the next few years. The one at the center of our Milky Way galaxy, using what is called the Event Horizon Telescope, which combines data from many radio telescopes worldwide, the collaboration of hundreds of radio astronomers from 34 universities and institutes, including the Institute of Astronomy and Astrophysics here in Taiwan, Taipei. The success is likely this decade. You can read about it on the web at that location. It's remarkable to me that the technology has become good enough that at that great distance of the center of our galaxy, we will likely, by the end of this decade, radio astronomers begin to image, produce images like the one of the black hole in Interstellar. Somewhat different because this is a much hotter disk. It's puffed up, it's not thin like the one in Interstellar, but somewhat similar to the one in Interstellar. And there also is a gigantic black hole in the nearest large, huge galaxy to our own large elliptic galaxy, M87. It's 2,000 times bigger and 2,000 times farther away than the Milky Way black hole, the 7 billion solar mass black hole, and that will also be imaged. Key to that imaging, because this is in the northern hemisphere, is a telescope being built, put together in Greenland, that again the Institute of Astronomy and Astrophysics here is involved in, which will bring in one component of the imaging that is done jointly by all these telescopes around the world. So this will take a little bit longer until this is but by early in the 2020s, I expect we will have images of 2 black holes, their disks and their shadows. Now, black holes are quite weird, as illustrated by Miller's planet. Miller's planet orbits around the black hole. As I said, 1 hour on Miller's planet is 7 years on Earth. And The problem, if the black hole does not spin, is that Miller's planet can be no closer to the horizon, to the whole surface, than this location. Why? If it's any closer, the orbit is unstable. You perturb it very slightly, and the black hole will fall in, the star will fall into a black hole. It's like standing a pencil on its end. If you stand it perfectly, it will survive, but if any small perturbation, it will fall over. So the innermost stable orbit, 1 hour on the planet is 1.5 hours on Earth. And that's not what we need for interstellar. So for interstellar, we need a fast-spinning black hole. For a very fast-spinning black hole, the whirl of space around the black hole makes the orbit stable. In some sense, it's centrifugal forces somehow tied into the whirling motion of space. And so 1 hour and 7 years is possible, but I have to tell you, when Christopher Nolan told me in one of our first meetings he wanted 1 hour on Miller's planet to be 7 years on Earth, I told him I don't think that's possible. He said to me, I've seen you be wrong before. Go do a real calculation. I went home, I did a real calculation, I discovered that he was right. It is possible that the black hole is fast enough. When the movie first came out, there were a number of physicists, astronomers, who criticized the movie because you cannot have so much slowing down of time near a black hole on a planet's orbit. Again, they didn't know about rotating black holes. They had not done the calculation. So there were some famous cases, well-known cases in that era where people backed off and said, okay, I was wrong. But it requires a very, very, very fast spin. So fast that it's not realistic in the real universe. It would be spun down just by capturing radiation. It would spin down. But our attitude in Interstellar was, if something is allowed by the laws of physics, and it is important for the movie, we will accept it. And even if it may not be very realistic, but at least it's allowed by the laws of physics. On this planet, there are huge waterways, 1 kilometer high. We don't have the audio. We lost the audio. Okay, well, you can watch this waterway without the audio. This water wave comes in, it descends on this spacecraft, and they struggle to escape from the planet before the water wave comes crashing down on them. This is the second water wave. They see 1 water wave every hour on this planet, 1 kilometer high. And so the question is, what causes these water waves? And just from the observation of them in this 1 hour period, I can deduce the following. The water waves must be tied to the deformation of the planet, just as the moon deforms the Earth's oceans to produce the tides. Similarly, it deforms Miller's planet, and it stretches the oceans on Miller's planet similarly toward and away from the black hole and squeezes them from the side. And it turns out that if this planet is not yet have one face always pointed toward the black hole, but is swinging back and forth because it has only gotten into this orbit fairly recently. And if the black hole weighs 100 million times what the sun weighs, then that rocking period is 1 hour, and the oceans will slosh back and forth once per hour, and you get these gigantic waves. From the large size of the waves and the 1 hour period, we can deduce how much the black hole weighs, and then from that we can deduce the circumference of the black hole's orbit. So interstellar is really very nice for physics, that you can look at what you see in the movie and you can figure this out, and you can figure out the black hole is spinning fast. So just from things you see about Miller's planet, you know how fast the black hole spins, you know how much it weighs, you know how big the black hole is. Inside the black hole, there are singularities. governed by laws of quantum gravity. And let me talk about that. I'll introduce it this way. Right at the horizon of the black hole, if you hover there, not falling in, you feel an infinitely strong gravitational force, which is why nothing can get out of the black hole. But if gravity is infinitely strong, then time stops at the horizon. It stops flowing at the horizon, according to Einstein's law of time warp. What happens inside the black hole? What can be slower than stopped time? Well, it's a little weird. What happens is time flows downward away from the horizon in what you would think is a space direction, but that really is a time direction. And in technical terms, that's inside the future light cone of anybody who's inside the horizon, going downward. And so that's another reason that nothing can get back out. Everything is dragged forward with the flow of time and cannot escape. So now I'm going to show you Cooper falling into Gargantua. Late in the movie, Cooper falls in. I really would like to have sound again, but somehow we seem to have lost it. Yeah, it's so he's falling into the black hole, and you hear him say, "I'm dipping down beneath the event horizon." And you look behind him as he says that, and so he's now inside the black hole. We're just going into the black hole at the moment. And still you can see the disk above him. So he has no trouble seeing out of the black hole, but we on the outside cannot see into the black hole. Why? Because light falls into the black hole to his eyes, but light cannot get out of the black hole to our eye. Another wonderful thing, and again this comes from the computer simulations, is that when he's down inside the black hole, here is the accretion disk. And the external universe now is inside the disk, and the black hole is outside the disk. Because basically as he went in, the disk, the black hole appeared to get bigger and bigger and bigger and bigger, and the disk shrinks down. And so the external universe that before was outside the disk is now inside the disk. And all of this is shown quite nicely in the movie. So again, some amazing things about relativity that come out accurately in this movie. Inside Gargantua, there is a singularity, and this is a diagram as seen by both beings. This is just my artist's conception of this singularity. It has a technical name, a BKL singularity. It's tremendously destructive. If you hit that singularity, you're dead. Your body gets torn apart in every which direction. You get stretched and squeezed in an oscillating way, first in one direction, then another, in a manner that's described by what is called a chaotic map in the theory in chaos theory. So really not someplace you want to go. But that singularity is governed by laws of quantum gravity. So this carries us into the modern era, the subsequent consequences of Einstein's relativity. That there is something here we would like to understand. We can understand what happens as you get close to the singularity. The final singularity we do not understand at all. It's governed by these new laws of quantum gravity that are obtained by combining general relativity with quantum physics. And this is likely some variant of what we call string theory. And understanding these laws has been the holy grail of theoretical physics since about 1960. So a great challenge for theoretical physics. And these laws control singularities inside black holes, the birth of our universe, whether or not time machines can be built to travel backward in time. These are very important laws, which we really would like to understand. Now, in the movie Interstellar, maybe let me back up. I guess I don't have it here. In the movie Interstellar, understanding those laws is a huge thing because Professor Brand needs to understand these laws in order to be able to figure out how to control gravity in order to save the human race. So frequently in the movie you hear the actors talk about the quantum data inside a black hole that they want. These are really the laws of quantum gravity that can be learned about by going down inside a black hole and making observations. And so this is what happens in the movie, is the robot cars observes the singularity and its properties, deduces enough about the laws of quantum gravity to be able to send that information back to Cooper's daughter so she can figure out from those laws how to control gravity and use it to save the human race. So again, this movie involves deep physics that if you're a physicist, you can see it there, but if you're not a physicist, you may not notice it. There, in fact, are 3 singularities inside the black hole, and Cooper encounters just one of them, what is sometimes called the outflying singularity or the shock singularity. And I'm not going to go into these details, but only to say that we've only understood in the recent years that there are actually 3 singularities in here produced by stuff that falls into the black hole, generating these singularities inside the black hole. Okay, I already commented on that. So, in my conversations with Christopher Nolan, he wanted to bring Cooper back to Earth from the black hole Gargantua faster than the speed of light. And when I told him that's not possible according to the laws of physics, he said, go home and do a real calculation. So I did. And I came back and said, no, here are reasons why you can't do it. He argued with me. He said, go back home and think some more. And after 2 weeks of this, he said, okay, I give up. I think I understand. He comments on this in the preface that he wrote to my book, my book about the science of interstellar. It was a very interesting interaction. So I suggested to him, instead, you can bring Cooper back through the bulk. And so let's talk about the bulk for a moment. String theory, if it's something like that is correct, requires that there are 6 or 7 higher spatial dimensions than just the 3 that are familiar to us. And one of them could be a large dimension, but something big enough to maybe even have some science fiction adventure. So to understand why this is called the 5th dimension in interstellar, here I show then our universe as a 2-dimensional surface, as I've shown it before, with one of the dimensions removed. In our universe we have east, west, north, south, and up, down as 3 dimensions. Time is a 4th dimension. And the dimension reaching out of our universe I call out, back, and that's the 5th dimension. So in interstellar, Cooper, when he falls into this, close to this outflying singularity, or shock singularity, he's caught by a vehicle called a tesseract, or hypercube, which has been placed there by the bulk beings who in the movie really do exist and inhabit